All right, so everybody, we're glad to have you here. My name is Hakeem Weatherspoon, and this is the monthly version of the Network Programming Initiative. We have Vishal Shrivastav, who's going to present today. He's going to present a paper that was published in NSDI 2019, Shoal Network Architecture for Disaggregated Racks. Vishal is a senior student, so he'll be on the market this year. So if you have a slot or you know somebody with a slot, please feel free to get back to Vishal. Also, just one other administrative note, Jen Rexford sent out an email about Slack, so if you have any questions, please send that along Slack, and we'll pause about 15 minutes or so and throughout the talk in order to take those questions. Okay, so let's go ahead and begin with Shoal and Vishal.
Okay, hello everyone. So today I'm going to talk about a new network architecture for disaggregated racks. So this is a joint work with folks from Hebrew University of Jerusalem, Microsoft Research, Walls Networks, Barefoot Networks, and Cornell. So today's data centers are built around these physical units called racks. And a typical data center has many, many such racks, all interconnected via a data center-wide network. And if you zoom into any one of these racks, what you would find is this stack of servers all interconnected via a top of the rack switch, which in turn is connected with the rest of the data center network. So this is how a typical rack within data center looks like. Now, in contrast, in a disaggregated rack, these servers are replaced by individual pools of resources. So you can have a pool of compute nodes, a pool of non-volatile memory, a pool of storage, a pool of accelerators, and so on, all interconnected via some internal rack network. Now, prior works have shown that disaggregated racks can have several benefits over traditional racks, such as you can get higher compute density, you can get fine-grained resource pooling and provisioning, seamless scaling of resources, and so on. However, disaggregation also poses some unique challenges for the rack's internal network. And the focus of this work is to resolve those challenges and build an efficient network for disaggregated racks. So one key way in which disaggregated racks differ from traditional racks is that in a disaggregated rack, you might need to connect as many as an order of magnitude more nodes than traditional racks. And what this means is that you can no longer use a top of the rack switch to connect those nodes. And in fact, you will need some sort of a network fabric to connect those nodes. And of course, this network fabric needs to be high performant in terms of latency and throughput, but perhaps more uniquely, it also needs to be power efficient. And this is important if you want to enable high compute density. So let me show you why. So if you look at a typical rack within a data center, it has some fixed power budget, as would be the case with any closed physical confinement. And for data center racks, this value tends to be around 15 kilowatt. And this power budget needs to be shared between the nodes that are doing actual computation and the interconnect that is your network. And so ideally, what you would want is for your network or the interconnect to consume only a fraction of this power so that you could use the remaining power budget to build these dense compute clusters. What you don't want is the opposite scenario where your network itself ends up consuming the majority of the power. Okay, so with these goals of high performance and power efficiency in mind, let's think about some of the ways in which one would go about building a rack scale network. So the first obvious way is to use, well, packet switch networks. And there has already been a lot of research done in designing packet switch networks that could give you low latency and high throughput. And one could potentially use one such design for rack scale networks as well. However, the problem with packet switch networks really happens on the other dimension. So the thing is that packet switches consume significant amount of power. And when you have a network of those switches or even a chassis of those switches, the total power consumption can very easily overwhelm the power budget of a rack. Now, on the other extreme, you have what are called direct connect networks. And these networks essentially get rid of the switching fabric altogether and just directly connect nodes with one another. So by design, these networks are extremely power efficient. However, when it comes to performance, their performance can be far inferior to packet switch networks. And this is because unless you have a full mesh topology, which is highly impractical, the packets over these direct connect networks are routed over multiple hops to the final destination. And this can have some serious throughput and latency implications for certain workloads. So if your workload is predictable, sure, you can build your direct connect network to work very well for that particular workload. But if your workload is highly unpredictable, like the data center workload, in the paper, we show that the performance of these direct connect networks can be far inferior to packet switch networks. So seeing that none of these strawman designs quite really fit the bill for a disaggregated rack network, in this paper, we propose a fundamentally different way of designing a network for disaggregated racks called Shoal. So Shoal is a network stack and fabric for disaggregated racks that is both low power and high performance. And the key feature that differentiates Shoal from the other strawman designs is that Shoal is built entirely out of fast circuit switches that can reconfigure within nanoseconds. So let me now discuss with you how we can use or how we can leverage these switches to achieve our goals of low power and high performance. So let's start first with the goal of low power. So Shoal's fabric is extremely low power precisely because its building blocks, that's the circuit switches, are extremely power efficient. And the reason for that is, unlike packet switches, circuit switches have no buffers, no packet processing pipeline, not even a serialization, deserialization circuit. So all they really have is a crossbar, which is used to set up connections between its input and output ports, also known as circuits. So as a result, a circuit switch consumes significantly less power than packet switches. But what about performance? Well, it turns out that the simplicity of circuit switches is really a double-edged sword. So while the simplicity enables low power consumption, now it also means that now you have to explicitly set up circuits before sending any packets over the switches. So if you contrast it with packet switches, in packet switches, this decision is made inline, right? As the packets are processed to decide where you should forward those packets. In circuit switches, you cannot do the packet processing anymore. So you have to first set up the circuits before you could send any packets. And this process is also known as the process of reconfiguring a circuit switch. And reconfiguration latency has been the real Achilles heel or the real bottleneck for circuit switching for a really long time. And the larger this value gets, the harder it becomes for your network to support low latency traffic or traffic that changes rapidly, both of which is the case with data center traffic. So if you drill down a little bit more into where this reconfiguration latency comes from, you would realize that it's really the sum of two things. First, the time it takes for you to decide what circuits to set up, and then the time it takes for the device to actually set up those circuits. And if you look at traditional circuit switches, well, those switches were actually bottlenecked by the device latency itself. So these switches took of the order of milliseconds to tens of microseconds to set up the circuits, which is pretty large. But what this also meant, the good thing that came out of it was that when it came to deciding what circuits to set up, now you could actually use a central scheduler to decide what circuits to set up. So this central scheduler could take your current traffic demand, run some optimization algorithm, and spit out the optimal set of circuits that you need to set up. So that was pretty easy. But regardless, the total reconfiguration latency of the switches was still very, very high to support low latency traffic. But more recently, there have been circuit switches commercially available that could actually reconfigure within nanoseconds. And what this means is now the bottleneck has well and truly shifted to the process of deciding what circuits to set up. So essentially what you need now is an extremely fast and high performance reconfiguration mechanism for the circuit switches. And the entire viability of these fast circuit switches basically hinges on whether or not you could come up with such an algorithm. So this essentially brings us to the first key contribution of this paper. So in this paper, we propose a fast and high performance reconfiguration mechanism for circuit switches. And this mechanism is actually inspired from works which were done in early 2000s in the context of load balanced monolithic packet switches. So in this paper, we adapt that idea and extend it to operate on top of an entire fabric of circuit switches. So let me next tell you how this algorithm works. So for simplicity, for now, we will assume that all nodes in the network are connected using a single circuit switch. And the key idea behind the algorithm is to use a static predefined schedule to set up the circuits. So this schedule has n-1 time slots, where n is the number of nodes in the network, and we call this n-1 time slots an epoch. And in every time slot, the schedule dictates what circuits need to be set up. For example, in time slot 1, circuit says that node A should be connected to node B, which is to say that node A can send a packet to node B. And so all the circuit switch does is simply set up a circuit between A and B. Similarly, in the same time slot, it sets up a circuit between B and C, C and D, and so on. So given this circuit setup, all the end host needs to do now is simply transmit the packet according to the current circuit setup. So the whole system behaves like one giant synchronous system. And later on, I will discuss some of the challenges that comes with that. But for now, let's turn our focus back to the static schedule. So if you look at these set of connections, these are nothing but just a permutation of all the nodes in the network. And what we essentially end up doing is just changing this permutation to build the entire schedule. Now, there is one key restriction in the way we select these permutations. And the restriction is that we select these permutations to ensure that every node gets to connect with every other node once every epoch. Now, this schedule has one very nice property. And the nice property of the schedule is that if, this is also sometimes called a cyclic permutation schedule. So the nice property of this schedule is that if your traffic, input traffic was uniformly load balanced, then transmitting packets according to this schedule would give you 100% throughput. So as an illustration, let's consider any arbitrary destination H. Now, if the traffic destined to H was indeed uniformly load balanced, then that would mean that every other node in the network would have some packet to send to H. So if we simply connect H to each of these nodes one after the other as dictated by the schedule, then H will keep receiving packets in every time slot and you will get 100% throughput, which is great. But of course, data center traffic need not be uniformly load balanced. In fact, data center traffic could exhibit any arbitrary traffic pattern. So what we end up doing is first convert that traffic pattern into a uniformly load balanced traffic. And once we have done that, we already know what to do next. So this is the key idea behind the algorithm. So the algorithm operates in two stages. So in the first stage, we uniformly distribute packets from each flow across all the nodes in the network. And in the second stage, those nodes forward the packets to the final destination. And the good news is that we can leverage the same static schedule for the load balancing stage as well, precisely because of the property of the schedule that each node gets to send a packet to every other node once every epoch. So let me show how this idea works in practice through a simple illustration. So in Shoal, every node maintains, every end host maintains n-1 queues, one per destination. And now assume that there is a flow from node A to node H. So let's see how that works. So in time slot 1, node A connects with node B. So node A sends the packet destined to H to node B as part of the load balancing stage. And node B buffers these packets in its queue corresponding to destination H. So a similar thing happens over the next two time slots. Now in the fourth time slot, node A connects with node E, but also node D connects with node H, which is the final destination. So in this time slot, both the stages of Shoal happen in parallel, which is to say that node A sends a packet to node E while node D forwards the packet to the final destination H. So a similar thing happens over the next time slot and the time slot after that, and H keeps receiving packet in each time slot and you get 100% throughput, which is great. But in general though, packets in Shoal traverse the fabric twice before reaching the final destination. So in the worst case, the throughput of Shoal's network can be 50% compared to an ideal packet switch network. And later on, I'll discuss how we compensate for this throughput loss. Okay, so this might be a good point to pause and see if anyone has any questions. Okay, so I'm assuming no one has any questions, so I will keep going. All right. Okay, so in the example that I just described, there was exactly one flow destined to a particular destination. So let's see what happens when there are multiple flows destined to the same destination, right? So for example, suppose that there is a flow from node A and node B, both destined to H. And let's for now just consider a single intermediate node C. So what happens here? So in time slot 1, node B connects to node C, so it sends a packet to node C destined to H, and node C buffers that packet in its queue corresponding to destination H. In time slot 2, node A connects with node C, and so node A sends its packet destined to H to C. And finally, in time slot 5, node C connects with the final destination H, and so it forwards one of those two packets to H. So you see what's going on here. So in every time slot, C receives two packets destined to H, but it can only forward one of those packets to the final destination. So over time, this queue will start to build up and you will get congestion. So what this really calls for is some sort of a congestion control mechanism on top of Shoal to handle this in-cast traffic pattern. So this brings us to the second contribution of the paper, where Shoal proposes a novel congestion control algorithm for a fast circuit switch network. Now, there have been a lot of congestion control algorithms designed for packet switch networks, but this is the first work where we propose a congestion control algorithm which is targeted specifically for fast circuit switches. And the trick here is, again, to use or rather leverage the static schedule that we have at hand. So for example, let's consider two arbitrary nodes A and C. So what the static schedule dictates is that A and C exchange packets in a very periodic deterministic manner. For example, in time slot 2, node A gets to send a packet to node C. Then in time slot 6, node C gets to send a packet to node A. And this process just continues epoch after epoch after epoch. So let's see how we can leverage this property to design a very simple and yet extremely efficient congestion control algorithm. So if you again go back to the previous example where C was our intermediate node and we had the queue for destination H at C, and let's assume that it already had a packet from source B. Now when it's A's turn to send a packet to C, then A would send that packet and C would buffer that packet again in the queue destined to H, and now the queue size has grown to 2. So when it's C's turn to send a packet back to A, it will piggyback on that packet the length of the queue to which the last packet from A was added to. So in this case, that length happens to be 2. And A simply uses this information to rate limit its flow so that there wouldn't be any congestion. So essentially what A ends up doing is it won't send any packets from flow A to H to intermediate node C over the next 2 epochs, and it will only send the next packet in the 3rd epoch. So this way it is guaranteed that the next packet from flow A to H would arrive at node C only after the previous packet from node A to H has already left C. So using this, Shoal is able to maintain an invariant that at any given time, there is at most 1 packet per source in any of these per destination queues. And using this, Shoal is able to give this very strong guarantee that each per destination queue in Shoal is bounded. And this bound is essentially governed by the current incast degree for that node. For example, in the example that I showed earlier, where the incast degree was 2, in that case, the per destination queue corresponding to H would be bounded by 3 packets, and it will never go unbounded. Okay. So let's see some of the challenges that arises with Shoal's design. So like I already mentioned, that Shoal operates like a synchronous system. So what this really calls for is a very tight network-wide synchronization. And second, the circuits in Shoal change very quickly at nanosecond scale granularity. So what this calls for is a very precise and very fast scheduler at the end hosts. Now, each of these challenges are extremely challenging in their own right, but thankfully there are existing solutions that we could leverage to solve these problems. In fact, 2 of my own works solve these problems So one of these works that was originally published at SICOM 2016 solves the time synchronization problem. And the other work, which was very recently published at SICOM 2019, solves the scheduling problem. Okay. So far, we have assumed that all nodes in the network were connected using a single circuit switch. But of course, in practice, that might not be the case. So in practice, what you might have is a fabric of circuit switches, low port count circuit switches. So how does Shoal work with this? Well, in the paper, we show that as long as this fabric is non-blocking, we can very easily break the network-wide schedule on the left into smaller schedules for each of these switches. So each switch independently reconfigures itself based on its own schedule. And as long as they do it in a synchronous manner, we ensure that the end-to-end connections would be the same as using a network-wide schedule. Okay. So let me summarize the key properties of Shoal. So Shoal proposes a fully decentralized traffic agnostic reconfiguration algorithm for circuit switches, which is shown to be extremely fast, which allows Shoal to switch at nanosecond timescales. Second, Shoal couples that with a novel congestion control algorithm that bounds every per destination queue in the network. Now, these properties do come at a cost. And the cost is that in the worst case, the network throughput for Shoal can go down to 50% compared to an ideal packet switch network. And to handle this, what we end up doing is just simply equipping each node with 2x bandwidth. And to see why this is a reasonable thing to do, we have to realize that bandwidth essentially translates to extra cost. Extra bandwidth translates to extra cost. And the fact that circuit switches are fundamentally much simpler than packet switches, in the paper, we do an analysis that even with 2x bandwidth, the cost for a Shoal network would be less or at the very least comparable to an equivalent packet switch network with half the bandwidth. Okay, so in terms of implementation, so Shoal is a clean slate design. So we had to implement our own network interface cards and circuit switches to verify the feasibility of the design. So we implemented it on top of FPGAs from Altera. And our circuit switch implementation could reconfigure in less than 6.4 nanoseconds. Next, we use these FPGAs to build a small 8-node testbed and verify that the queuing and throughput properties of Shoal also hold in practice. In terms of evaluation, so we evaluated Shoal based on the two design goals of low power and high performance. And in terms of power, we were able to show that Shoal consumes 3.5x less power than a packet switch network for a 512 node rack. And this is after accounting for the fact that Shoal has twice the number of switches because Shoal has 2x bandwidth. In terms of performance, we used a packet level simulator that was written in C and cross-validated with our prototype to run 5 different disaggregated workloads on top of that simulator. And what we were able to show is that for each of those workloads, Shoal performs comparable or better than several recent packet switched network designs. Here, performance is measured in terms of flow completion time or latency for short flows and average throughput for long flows. So there are a couple of things that I would like to point out here. So in terms of the tail latency, Shoal significantly outperforms other packet switch network designs. And this is a direct consequence of Shoal's congestion control algorithm that allows for bounded queuing in the network. In terms of throughput as well, Shoal significantly outperforms packet switch networks. And this is partly because Shoal has 2x bandwidth. So if you remember, we equipped Shoal with 2x bandwidth to account for the worst case traffic pattern. But in practice, worst case traffic pattern doesn't always happen. In fact, the traffic pattern keeps changing dynamically. So on average, Shoal ends up getting more throughput. So one other way of looking at this result is that if you build a network, a packet switch network, and a Shoal network with comparable cost, then you will end up getting more throughput in Shoal network. Okay, so to summarize Shoal, so Shoal is a network that comprises entirely of fast circuit switches. And at the physical layer, it uses a static predefined schedule to configure these circuit switches. And end hosts simply transmit packets based on the current physical circuit setup. Now, this calls for two key requirements: that the network is very tightly synchronized and that you have a very fast and precise scheduler at each end host, both of which we show is quite achievable by leveraging prior works. So on top of this physical network, Shoal proposes a routing algorithm and a congestion control algorithm, using which we show that the entire network can achieve very high performance. And we give a real-world implementation of the entire system, which includes implementation of the circuit switch, the end host NIC, and all the algorithms on top, which is the routing algorithm, congestion control, scheduling, and time synchronization. So to put all this together, Shoal is the first end-to-end network design for a network that is built entirely out of fast circuit switches and is shown to be low power and high performance. And the reason why I find this work extremely exciting is because there is actually a bigger picture here. So if you look at the data center bandwidth demands, it has been increasing exponentially over the years. But if you compare it to the capacity of the packet switches, that has been growing much more slowly because of the slowdown in Moore's law and the end of Dennard scaling. So essentially, there has been this growing gap between the bandwidth demand and the packet switch bandwidth capacity. And this is where circuit switching can come in to save the day. So optical circuit switches give you this promise that you can switch data in a completely data rate agnostic manner, which is to say that if as your link rates increase from 10 Gbps to 40 Gbps to 100 Gbps to 400 Gbps, you do not need to change your network fabric at all. So your network fabric is essentially bandwidth agnostic and can essentially support any line rate. So that's the promise of optical circuit switches. And to be honest, this is not really a new observation. People have known of this promise for a long time, but the Achilles heel or the bottleneck has always been that reconfiguration latency. So if we can somehow combine this promise of optical circuit switches with fast switching, like we propose in Shoal, and it's also proposed in a similar paper called RotorNet from UCSD, what we can get is this, in principle, we can build a data center network that not just provides extremely high bandwidth, but is also high performance. And while I admit that there are some impending challenges that would need to be resolved to make it a reality, but nevertheless, the promise is very much there. So on that note, I would like to thank you all for your attention, and I'll be happy to take any questions.
Vishal, this is Jack Bressel. Can you hear me?
I can hear you, Jack. Vishal, can you hear Jack?
Let me check on Vishal real quick.
I think Vishal has muted himself.
Hello?
Hi, Vishal.
Can you hear him?
No.
Okay.
Give us just a second, Jack. We're running around in the CS department to grab Vishal.
Yeah, okay.
Ah, we hear you now. Do you hear Jack?
Hi, Vishal.
Hi, yeah.
Just a quick question. Thank you very much for the talk. I apologize. I came in a little late, so I might have missed a little bit of the run-up.
Mm-hmm.
I have a question about some of the optical switching technologies that have been proposed, such as RotorNet.
Mm-hmm.
So challenges with RotorNet seem to be that it essentially had a fixed sort of round-robin scheduling mechanism that would be awfully hard to change, it seemed, in practice. Do you have any thoughts about the viability of that kind of technology in practice, in a setting where obviously the, sort of a data center or cloud setting where the number of interconnected nodes would be changing, possibly fairly frequently?
Right. So the question about the static scheduling actually is the main. So you mentioned RotorNet, right? So RotorNet is very similar to Shoal, and actually the main contribution there was to actually show the viability of the static schedule itself, that even using a static schedule, you can actually get very high performance over these networks because it's traffic agnostic. The way we use it is essentially traffic agnostic. Now the problem that you mentioned could be that what happens if the number of nodes in your network change. So if the number of nodes in your network change, then you will have to change the schedule at each of these switches, essentially to account for the new node that has added or the new node that has been removed. So for that has to be done offline. So you cannot do it online as your nodes change. But if the number of nodes is stable, or it does not change that frequently, then the static schedule is supposed to work pretty well.
Okay, thank you.
Cool.
Hey, Vishal, this is Jim. Can you hear me?
Yes, I can hear you.
So when you gave this talk at the IAP, or you talked about Shoal at the IAP workshop in May, Hakeem and I were there, and
Yes.
The industry guys were pretty excited. They voted you the best poster. So congratulations, but I'm just wondering what kind of response are you getting from other industry people on this solution?
Actually, I haven't had a lot of chance to talk to industry people out of the IAP workshop that we had. So I can't really comment on that. Are there any more questions?
There are no more questions on Slack.
Okay, so should we end?
Yeah, since there's no more questions on Slack and there's no more question directly online, we'd just like to thank Vishal again.
Yeah.
Again, this is recent work, and if you'd like to follow up with him afterwards, just please feel free to send him an email. Thank you, everybody, and have a good Thursday and Friday.